Alright. You don't really need to know this. Um, I test more of this knowledge on chemistry, but let's see if I can find the mnemonic. So how I remember the gas law is, my internet is super wrong, is Charlie Brown is a TV show. Boys play video games. And Gay Lussac uses TP on the Maypole. Do you know what Maypole is? So, have you ever seen like Renaissance festivals where there's a pole in the middle and then you see a lot of dancing people with ribbons going up to it and spinning around in a circle? That's called a maypole. Gay Lussac, so cheap, he uses toilet paper. So, Charles's law relates temperature and volume. Boyle's law relates pressure and volume. And Gay Lussac's law relates temperature and pressure. So Charles's law states temperature increases, volume increases. He discovered that temperature divided by volume is equal to some constant. In other words, temperature is directly related to volume. In more math speak, we could write it as temperature is equal to some constant times volume. This is a direct proportional to. So this is a direct relationship. Another way of writing this is that temperature let me draw this symbol better. Is proportional to volume. This means proportional to. So if you double the volume, you double the temperature. We could use this fact to come up with the equation that the initial temperature divided by the initial volume has to equal the final temperature divided by the final volume. I usually use subscripts 1 and 2, 1 being the initial and 2 being the final. I'll stick with that. Because it never changes, it's constant. Similarly, we could go and Boyle's law. It says as pressure increases, volume decreases. So this means that pressure is inversely related to volume. So if you take the product of the two is equal to some constant. So if you wanted to make an equation, another way of doing it is pressure is equal to some constant divided by volume. Another way of relating it is pressure is inversely proportional to volume. So this notation, this whole thing, means inversely proportional to. As you double one, the other one has to decrease by half. And we can come up with the equation that pressure 1 times volume 1 has to equal pressure 2 times volume 2, because this product doesn't ever change. And lastly, we got Gay-Lussac. As temperature increases, pressure increases. And I should note one thing I haven't done. This assumes constant pressure. This one assumes constant temperature. And this one assumes constant volume. So these laws only apply if the third variable is held constant. So same thing, temperature. And I really should switch these around. I am. I'm going to put pressure on top divided by temperature is equal to some constant. So pressure is equal to some constant times temperature. So pressure is proportional to temperature. And we can do I don't like how I've done the equations, but it's alright. Pressure divided by initial pressure divided by initial temperature is equal to final temperature. Pressure divided by initial temperature. I don't like how I've done the equations because of the combined gas law. So let me redo that. The combined gas law states, if we combine all three equations, we get this. Pressure times volume divided by temperature is equal to some constant. This is because pressure divided by temperature is equal to a constant. This is from Gay-Lussac. I should capitalize his name. And volume over temperature is equal to some constant. This is Charles's law. This is how I should have written it, so that you can clearly see where the laws come from. And pressure times volume is equal to some constant, and that's Boyle's law. So we can see from this equation that they all are contained in it. And it works out that we can combine all three of these into one equation. Note though, however, these constants are not all the same K. It doesn't matter though what the constant is, because we're going to ignore the constant and just know that initial pressure times initial volume divided by initial temperature is equal to the final pressure times the final volume divided by the final temperature. This is how you can combine them. I recommend you memorize just this equation. And if one thing is not mentioned in a problem, then you can just remove it from the equation. So if I says what happens to temperature as volume increases and I don't mention pressure, you can assume pressure staying constant. In which case, this just becomes V1 over T1 equals V2 over T2. This is going to be your Charles's law. So let's think of some examples of everyday things. What would make sense? Let's think of an aerosol can. This is not accurate. Oh, another thing, I should go back. Constant mass on all of these. Even the combined gas law. This assumes constant mass. This example doesn't have constant mass, but the amount of mass is not that important. Let's say you have a can of deodorant and you spray some of it. What happens to the pressure inside the can? So it's going to decrease. What happens to the volume of the can? The can doesn't change shape, so we can assume it stays constant. Now, technically, though, in a deodorant can, we have a layer of liquid and a layer of gas. And there's a straw coming down here to the liquid. And what's happening is the volume of the gas is decreasing. But we can assume that not by very much. What is changing, though, significantly more is the pressure. And what happens as pressure decreases? What happens to temperature? decreases. So have you ever sprayed a can of deodorant and felt it get really cold? That's because as pressure decreases, the temperature has to decrease. Again, this is not a true explanation because mass is changing. We can't really apply this law. So this really, we can't make that assumption, but it's close enough. As you're driving down the highway, again, we can't really apply this law too much. But as you're driving down the highway, what happens to the gas inside your tire? It gets hot, so temperature is increasing. What happens to the pressure? It will increase. Which means if you go to your car and air up the tires with it never being drove, and you get it up to max pressure, and then you drive it down the highway, you risk blowing it out. Because you didn't account for the fact that it's going to increase the pressure. If you have a mild flat or a very slow leak, whenever you start driving, it can go up to normal pressure temporarily. This is where the combined gas law goes into effect. The volume would also mildly increase, which would cause the pressure not to increase as much. So if we assume the pressure stays constant, then as the temperature increases, the volume will increase too. So if the pressure isn't changing that much, then the volume won't increase. Once the volume has gotten to the most size, then the volume stays constant, and then pressure starts going up. So what would happen if you have a balloon and you put it in a freezer? It shrink. The temperature of the gas goes down, so the volume of the gas will go down. What's some other examples? So I've stated that all pressure really is, and I don't really do this in this class, but we should actually analyze this. But you should keep in the back of your mind that force divided by area is pressure. So we have a surface. We have like a tile on the ground. What's happening is particles are coming down and hitting it and bouncing off. They're transferring their momentum to the tile and to the earth, but this is equated to a force. And how much force is being applied over some area is your pressure. On Earth, that is 14.6959. Around atmospheric pressure is 14.7 pounds per square inch. So every inch in your body has 14.7 pounds of pressure pushing on it, keeping it down. Let's see. So let's do an example. I should go over these. So 1 atmosphere of pressure is the atmosphere we can see when we're at. It's at sea level. Technically, depending on where you're at, it can change. This number is equal to 760 millimeters of mercury, 101.325 kilopascal as a period. If I remove the kilo, that becomes a comma, which is also equal to torr, 660 torr, or 14.7 psi. Torr and millimeter per mercury was changed so that torr matches millimeters of mercury. You might be wondering what a millimeter of mercury is. Do you know what that is? Imagine you had a bowl of mercury. So we have a bowl of mercury. And suppose I place in it a glass tube. And let's say that I have no air or anything in this tube. So it's a complete vacuum. So, vacuum. Where are all the forces being applied everywhere? Let's say this is mercury. Well, all the force is being applied on the mercury. It's technically being applied to the glass, but the glass is a rigid object. It can't move or bend. If too much force is applied to the glass, it will break. There is no force inside, so we can ignore the force on the glass. And the only thing that's able to move is the mercury. And so it's going to push the mercury down. Since there's no air here to push it down, it's going to float up the chamber. So we're going to end up having the mercury flow up in here because that's the only force going on. We also have the force of gravity. Gravity is going to pull down the mass of that column times the acceleration due to gravity. And when these two forces counteract each other, the mercury will stop and we'll have a vacuum up the top. If you measure this distance, if you measure it in millimeters, and we're using mercury for 1 atmospheric pressure, we measure 760 millimeters of mercury. So, all which is equal to 76 centimeters of mercury, or 0.76 meters of mercury. Why don't we use water? So if we replace the setup with water, water, and we get a long tube, the water is going to be pushed down and flow up. If we measure the distance between here and where it stops, note water isn't a very good thing because its boiling point at these pressures is extremely low. So it'll actually start boiling and this will fill up with water vapor. So it's very bad to do that, but we get a value of 33.932416 carried feet. So I want you to think about that, of how long of a tube that would be. So about 34 feet. You couldn't fit that in a doctor's office. And also, as this lowers the pressure, it will start boiling here. So that's not good. Mercury is very dense. Water doesn't have that much density. So the mass component here isn't strong enough to counteract it. You need 34 feet of. You take about 34. You have to count the fact that this is no longer a vacuum. As pressure builds up in here, you have another thing of pressure going down. So let's suppose Suppose you had a bottle, an empty water bottle, whose volume is, let's make it 600 milliliters, and is left in your vehicle at 20 degrees Fahrenheit, 20 degrees Celsius, which is 68 degrees Fahrenheit. Suppose the temperature drops to freezing point, 0 degrees Celsius, which is 32 degrees Fahrenheit. What is the volume of the bottle? When I say empty, it is filled with gas. So what equation will we use? Alright, we can assume that the pressure inside the bottle is going to stay constant. So what gives the bottle its shape? So we have a bottle of some shape. What maintains the shape is because it's filled with some gas at some pressure, and that pressure is pushing on the outside of the bottle. And if the pressure on the outside stays the same, then it'll keep its shape. Plastic is not very rigid, so if we decrease the pressure inside, it's going to change its shape so that the pressures on the inside and outside match up. Note that we need a net force of 0 for things to have no motion. Since the bottle's not going to be constantly squeezing and vibrating and moving, it's going to eventually stop. That means the pressure inside and the pressure outside has to match up. There is another pressure that we're not going to worry about, or another force. This is the internal stresses of the material. It's the reason why you can have a steel drum and remove all the air from it, or you can have a glass container and vacuum out all the air. Glass is rigid, so as we try to bend it, what happens is the internal stress forces are going to go. So on the molecular level, they pull upward, and we end up that this pulling upward inside the material keeps it straight. And so forces on the outside and inside can be different, but for plastic, since you can bend it, we can assume that the pressure is going to stay constant. So the initial volume is 600 milliliters. The initial temperature is 20 degrees Celsius. But is this a delta T? So that means we have to convert it by adding 273.15. So that's 293.15 Kelvin. The final temperature is thus 0 degrees Celsius, which is equal to 273.15 Kelvin. So we can cross multiply. Volume 1 times temperature 2 is equal to volume 2 times temperature 1, cross multiplying. And solving for volume 2, we can divide both sides by T1. which cancels out on that side. So the final volume is equal to initial volume times final temperature divided by initial temperature. So 600 milliliters times 273.15 Kelvin divided by 293.15 Kelvin. Kelvins cancel out. This also illustrates why you have to use Kelvin, because 0 degrees Celsius, if I put 0 on the bottom, which I know 0 goes on the top here, we get the volume of 0, which obviously is wrong. And if you put 0 on the bottom, you can't do that in math. This is the reason why the Kelvin scale was invented, so we can do mathematics. We can see that the new volume is 559.065 milliliters. So 559 milliliters. The bottle has strength. Make sense? There's another law that's called the ideal gas law. The ideal gas law is pressure times volume is equal to nRT. We can see by rearranging this, pressure times volume over T is equal to some constant. This is the ideal gas law. I mean the combined gas law. And if we notice, this K is actually N times R. R is the gas constant. And N is the number of moles. And moles have I explained moles very well? So 1 mole of oxygen, O2, is 6.022 times 10 to the 23 O2 molecules. It's like a dozen. 1 dozen O2 molecules is equal to 12 O2 molecules. It's just a mole is significantly bigger. And since each molecule of oxygen has a mass, this can be done by mass. The thing about gases, though, is it doesn't really depend on mass, it depends on how many particles you have. One thing we assume in ideal gas is the particles are so small compared to the container that we assume they're point-like objects. So it really comes about because of the number of particles. So let's assume that pressure is equal to 1 atmosphere, and the standard temperature. So let's actually change this. 101, 325 Pascal. And the temperature is 273.15 Kelvin. These two values are known as standard temperature and pressure. The R value my internet's working well enough to look it up. So R is equal to 8.3145 joules per mole Kelvin. It's also equal to a liter times Pascal, or 8.3145 liter times Pascal divided by mole Kelvin. These liter times Pascal is a joule. Is equal to 0.0820574 liter times atmospheres divided by mole Kelvin. This is if you're in atmospheres and liters. R, it's equal to 62.3636 liters times torr per mole Kelvin. So if you're in torr, atmospheres are pascals. There is one other unit I haven't mentioned. 1 bar is equal to 100,000 Pascal. So that means that 1 atmosphere is roughly the same thing as a bar. Because a atmosphere is 101,325, so it's only off by like a percentage, 1%. So solving this for number of moles, N equals PV over RT. So we'll use Pascal and Kelvin. So that would be pressure is 101,325 Pascal divided by R, 8.314 joules per mole Kelvin times a temperature of 273.15 Kelvin times volume. This equates to the number of moles is equal to 440.6175 times your volume. So if you have, so the unit for this would be moles per liter times volume. So that means there is 44.6 moles in every liter. At STP. So if you have a 2-liter bottle, you can actually count how many particles is in it. You can work this out also changing the temperature and the pressure to get more accurate values. But this is a nice little way of relating or figuring out how many moles is in a container. I think that's enough introduction to it. we'll go ahead and pass out the homework. We'll work on more examples on Monday, but I think you should be able to do everything. You're smart enough to figure it out without me going through every single possible scenario. It's literally just plug it into the equation.